Okay, so now I want to continue the discussion from last time. I want to start by maybe going over a little bit of what Peter said, perhaps adding some details or some explanations. So the main topic is normed analytic rings. So we had this, now we've officially defined this framework of analytic stacks that we're working in. And we saw that there was an embedding of, light condensed anima. At least a functor. We saw that there was a functor to analytic stacks. And it's induced by, so these things are generated by light profinite sets. So say T. And to one of those, you assign, I'm just going to write it. I know this is probably overloaded notation, but you have this discrete ring of, this is a discrete ring of continuous functions on your profinite set with values in the integers. It's a discrete ring. And you can view it with the maximal analytic ring structure, so uncompleted. So you look at all condensed modules over this discrete ring, or derived condensed modules over that discrete ring. And that's the analytic ring that you associate, and then its spec is an analytic stack. And the thing that makes this functor nice is that this assignment here, this sends hypercovers to Schriek hypercovers satisfying Schriek codescent or descent.
So apparently, I don't know, but we proved that those are equivalent. Schriek descent and codescent was one of the talk.
Oh, it's the exact same argument. You mean in the hyper case, or?
Okay. I remember Peter referred to something like this in some explanation. So that when you have a Schriek, you can formulate one that the category is equivalent to the one to the inverse limit by Schriek, or by the direct limit by lower Schriek, and those are...
It's a purely formal fact about PRL, so proved by Lurie that those are equivalent. So it doesn't need anything on the shape of the diagram or whatever. Yeah. So it's so these were the things that which defined the notion of analytic stacks. But it also preserves finite limits. So for example, pullbacks. Well, let me say finite limits. So if you take a pullback of light profinite sets, that's just a filtered inverse limit of pullbacks of finite sets, and then it goes to a filtered co-limit of the same situation for finite sets. So this reduces to finite sets, and for finite sets it's kind of completely clear. And those two facts kind of imply that this functor here, so that the induced functor here that you get from this, so this is a co-limit preserving, co-limit and finite limit preserving. Which is nice. Now I want to mention that there's a paper on the archive by Rok Grigorich. So he studies the analog of this. With analytic stack replaced by FPQC sheaves. In usual sheaves, FPQC sheaves in usual algebraic geometry over a field. And he wrote a nice article which he recently posted on the archive, which goes into some detail about properties of, well, I mean, he's working in a slightly different setting, but much of it is the same. Yeah, so I would recommend reading that. Okay. Right. Okay, and then so the other example that Peter discussed was example of a light condensed set. Let me start with this setting. So let's say K is a compact Hausdorff.
I think that the question in the chat.
Yes.
How does one recover a topological space from the associated analytic set? Is it the set state of points in some suitable sense?
So I don't see that there is a well-defined notion of underlying topological space of an analytic stack. So
in usual stack,
I can't take the right joint of this function.
yes, that's right. It's you have an underlying light condensed set, but I don't see an underlying topological space. Oh yeah, I guess then you could map this to topological spaces. Okay.
so
Yeah.
you have underlying. So when you have a stack, no, the stack is something with. It's a generalization of ring spaces here, but what is the topology? No, I'm not.
Well, we're not really using.
Like a diagram, you cover by kind of your formal spec of analytic
Yeah.
rings, then you have the world simplicial diagram of such
Yeah.
things, and
Yeah.
then how do you get a space? How do you get you cannot take spec in the although I think you can consider all open substack. Maybe it makes sense in your setting to consider open.
Yeah, you could use monomorphisms of analytic stacks to try to. There's different ways to. Okay, there's actually different ways to try to extract an underlying topological space from an analytic stack, and well, yeah, I'm not sure it's worth saying anything completely general in the world of arbitrary analytic stacks, but well, when we introduce this notion of normed analytic ring, we'll see that when you have a normed analytic ring, then there's a nice way of extracting underlying topological spaces for things over that normed analytic ring. Let me continue the story, having unsatisfactorily not addressed the question. So let's so if you have a compact Hausdorff metrizable, and let me add finite dimensional. And this actually is the same thing as saying that K is embedded as some closed subset of some finite product of copies of the closed unit interval. So these things are very easy to imagine. Then we can view this as a light condensed set, in particular a light condensed anima, and then we get an associated analytic space. And Peter made a claim about the functor of points for this, for the analytic space associated to such a K. Well, or maybe there's two claims. So, and two claims. So the first is that. So first of all, what's the most important invariant you have if you're given an analytic stack? It's its derived category. So we saw that Schrieg descent implies star descent, which means that the derived category of a stack is well defined by pullback, upper star pullback, this D of K, I mean the analytic stack associated to K by abusive notation. This is just sheaves on K with values in derived abelian groups.
Okay.
What's that?
That's abelian groups.
Thank you, yes. Thank you. And more generally, if you base change this stack to an analytic ring, then you put D of R there. Right. And the second claim is that if you want to map, say, spec R for an analytic ring R, to this k, this is equivalent to giving a symmetric monoidal functor from sheaves of now not condensed abelian groups to D of R symmetric monoidal colimit preserving functor such that Schriek locally on R, on spec R. What's that? Oh, thank you. Yes, yes, yes. DZ linear. Yeah. Such that Schriek locally on R, we have that f of the connective part, so sheaves k with values in, say, d of z greater than or equal to 0, lands inside d of R greater than or equal to 0, the connective part there.
So how much where is the finite dimensional use? Is it some technicalities about, I don't know, you can define the analytic stack for any case such case without finite dimensional.
Right, right. So the finite dimensionality, we're going to see where the finite dimensionality comes in. I'm going to sketch the argument for this. Well, the first remark I want to make is that the left-hand side is a set. Well, maybe I'll say both are sets. So we're in this world of analytic stacks, which is based on some sheaves of anima. So a priori, everything is an anima. I mean, your k is implicitly some colimit of things and could be introducing higher homotopy. But because of this property that this functor preserves pullbacks, this is a monomorphism in condensed anima, in light condensed anima. So by the property of and monomorphism means when you pull it back along itself, you get itself again. Nothing fancy. Then you get the same in analytic stacks. And that tells you that if you have two maps can agree in at most one way, so you have a set and not a general anima. And over here, the reason this complicated looking space of functors is a set and not an anima is that, it's d of z linear, so it's actually the same thing as just if you take, I don't know, sheaves of anima and you just ask for a colimit preserving functor like this. And then this is generated by these, like the representable ones. If we, so in particular over here, everything is determined by what it does to the free things on these representable guys. But then we can pass to the complementary closed, and it's also determined by the so this thing is determined by where it sends the constant sheaf on a closed subset. And then this should just should be an idempotent algebra. In the target. Or should go to an idempotent algebra. Under F, it should go to an idempotent algebra in the target. And then you just have to have some conditions that are satisfied. So you just have to specify a collection of idempotent algebras in the target, and then some conditions have to be satisfied. So let me write down here. So this is what implies that left-hand side is a set. But on the right-hand side is just the set of maps from, you have closed subsets of K to idempotent algebras in D of R. such that filtered intersection goes to filtered colimit, and union, union goes to, well, the analogous construction. So there's if you have a union of closed subsets, you can kind of use a Meyer-Vietoris to express the constant sheaf on the union in terms of the constant sheaf on the two pieces and the intersection, and that gives kind of an algebraic formula for what the value on the union should be, which you can write down just at the level of idempotent algebras, and you ask that union goes to that algebraic construction you have here. And then you still want this condition here, but that's just another condition.
So this looks like sheaves on K with variable BZ. This looks like the direct category of K.
The direct category of sheaves on K, yeah.
Yes, and
yeah.
This uses the finite dimension.
Yes, that does, yeah.
Okay, and then the equivalence with sending various pieces, the equivalence of giving something on closed subspaces, this doesn't use finite?
No.
So when you work with which one, with sheaves or with the derived?
So far I haven't used finite dimensionality. If you take this in the sense of Lurie, then everything I say works generally. Okay. So for, I think, an arbitrary topological space K, but certainly for a compact Hausdorff space. Okay. Right, and so the point is that idempotent algebras form this is actually just a poset. So there's a priori it's an infinity category, but one checks that it's just a poset. So a map, if it exists, is you can uniquely write it down. So then we just have the right-hand side is just you just have to give a map of posets to specify all of this. A map of posets satisfying some simple conditions to specify such a symmetric monoidal blah 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 functor, and so on. The next thing to note is that, okay, we should now I'm claiming these two sets are in bijection, and I should first write a map, and the map in this direction is obviously going to send f to f upper star, where f upper star is so, well, a priori, d of k, well, d of k is this thing, but we can restrict to the full subcategory where you require the values to be discrete. Or I could say d con z linear functors from sheaves on k with values in d con z. And then, but I should, that gives one of these things, but I should maybe explain why the, that's the derived category of condensed abelian groups.
Light condensed,
Yeah, light, yeah.
Okay, so you have so F goes to spec. By definition, spec out to K is a map from the. So first you have to give a map on the ring of. But this is part of this functor. The map on rings is included in knowing the. No.
So what is it you're?
No. A map F from spec R to K means that you have a map of analytic rings.
Well, it means you have some, say, Schriek hypercover of this, and a map of that Schriek hypercover to the hypercover of this by profinite sets.
Because K set is not okay.
Yeah.
Okay. And if K is totally disconnected, then it is the same as a map of...
If K is totally disconnected, yeah, so maybe, yeah, if K is profinite, then the left-hand side is the same as a map of rings from continuous functions on K with values in Z to just the underlying ring of this analytic ring. That's by construction that those are the same. Okay, and this actually explains why this condition is satisfied, I mean for arbitrary K, because for arbitrary K you can surject from a profinite set T, and then this is a surjection, so by definition there will be some Schritt cover of spec R where you factor through a map to T. But once you factor through a map to T, then your F upper star is just being induced by this functor. But this is just a filtered colimit of filtered colimit of C of like Kn Z's, where this is finite. Well, what do I want to say? What I want to say, maybe, yeah, I don't know if that's the right remark to make. So in the case when K is profinite, then, so you want to prove that the image of every connective object is connective. What do you know? You know that the image of the unit is connective, because the unit has to go to the unit in D of R, which is this underlying ring, which is connective by definition. But then on any Clopin subset, we'll then have to go to something connective because it will be a retract of that unit. But then the Clopin subsets generate the connective part under colimits because they generate all open subsets under colimits, and then everything is generated under that by colimits. So everything will be, in this thing here, in the case where this is profinite, everything here will be a colimit of retracts of the unit objects, and therefore will land in here, in the case where K is profinite. So in this case, the connectivity is automatic. So that's why this is a well-defined map. If you want to go backwards, so given such a symmetric monoidal functor or such an association with idempotent algebras, it's enough to go backwards assuming this condition, because you can work Schritt locally because both sides are Schritt sheaves, or satisfy Schritt descent. So to go backwards, conversely, if you're given such a symmetric monoidal functor, let's see. On the connective level, then you want to produce this map here. What you can do is you can take, oh, sorry, this was K. You can take this hypercover, take a hypercover by profinite sets, or just, well, I guess just a cover is fine. Once you start with a surjection from a profinite set, oh, sorry, what am I doing? Each of these will automatically be profinite sets because they'll be closed subsets of the product of two profinite sets. Then you get a corresponding diagram of rings commutative algebras in D of R greater than or equal to 0. So you just take, so if this is pi, so pi 0, and then this is pi 1, and then pi 2, and so on. So you have pi 0 lower star of the constant sheaf, pi 1 lower star of the constant sheaf, and so on. You have the constant sheaf. And these things are all going to be connective. And in fact, you have a Kunith formula. Which gives that this is this thing is the, well, I get a check, the co-check nerve, I don't know, of just the first map. So because these maps are proper, any map of compact Hausdorff spaces is proper, using proper base change, you can see that like the whole diagram is just determined by the first part. And now you can apply your symmetric monoidal functor f. So you can take f of this pi 0 lower star z. And now this is a commutative algebra object. Well, first of all, I should be saying r pi lower star z, but it's actually concentrated in degree 0. Yeah. Yeah. And then, in fact, you can say, so, in fact, animated. So it's not difficult to produce the animated structure, but let me not get into it. And then you take to R prime to be the analytic ring defined by f of pi 0 lower star z modules. And then just the induced analytic ring structure of you just take this ring object in here and look at that underlying ring and just modules over that ring in the thing you already have. And then you can check that this procedure induces a map from the check nerve of this R prime mapping to R, so spec R prime mapping to R, to spec R. And then by the construction, you get an
So is this the underlying Z the same as Z of H of U?
I'm sorry, where are we?
On the top board?
Yes.
The underlying Z.
Yeah.
And then you have Z
right.
H U. Are they the same?
They are not the same. So this one maps to the constant sheaf Z, and that one's the cofiber when Z is the complementary closed subset to the open subset U. So they're not the same, but they determine each other in a canonical way.
So you said something to the effect that pi 0 lower star Z, so this is actually a single sheaf. In any case, it's a commutative algebra object in some derived, and then F, because of it's defined, is a symmetric monoidal, so you get some commutative algebra object in some derived, like in in fact, you say there is a canonical way to view it as a simplification.
Right.
But this is not. I think in characteristic 0 it should be.
Yes, in characteristic 0, it's clear.
Not because of the abstract way you define, you have the condition. It's not clear that you.
That's right. Yeah, it requires a little extra argument. So you can see, for example, that. Yeah. It requires an extra argument, but so probably the work that you're doing with Maxime will make it more clear. Because what is being probably carried out at the moment is a kind of a categorical perspective on animated commutative rings, so that you can single out what properties of the derived category of an E-infinity ring, or the category, should just say category of modules over an E-infinity ring, what structure do you need to put on that to promote the E-infinity ring to an animated thing. And it's something like derived symmetric power functors. And you have them on I mean, maybe there's an even simpler argument. Sorry. I think in this case there might be a simpler argument. So you want to produce a, sorry. Let's leave that aside for the moment and address it at the very end, okay? So yeah, yeah, sorry. Okay, so where are we? Yes. So then what we get is a map from the check nerve of spec R prime mapping to spec R to the check nerve of T0 mapping to K. And then we're going to be, then we'll have produced a map by descent, we'll have produced a map from spec R to K. So then if we just, so as long as we know that this is a cover. Okay. But note that this is a proper map. By construction, we built it as something where the, so to speak, the completeness condition isn't changing when you go from R to R prime. You're just extending the ring. So by the criterion we had for shrinkable things, it's enough to see that the unit object, which is R triangle, lies in the category generated by the image of, so in the image of the forgetful functor, sorry, d of R prime to d of R. And for that, by applying F, it's enough to see
using
yeah, the lower shriek, but lower shriek is lower star, so it's really just the forgetful functor from.
And the image, this means the image, and
closing by say finite, yeah, by cones and retracts and some finitary operations. Yeah. Okay. Then applying F, it's enough to see that the constant sheaf on K is in the subcategory generated by the lower star functor. So, sorry. Sorry, sheaves of T on T naught with values in DZ. So pi lower star, sheaves on K, values in D of Z. Okay. Or in Keel-Matthews language, we need to see that pi lower star of the structure sheaf on T0 is descendable. Right. Now remember that this was kind of, we could choose this arbitrarily. So it's actually enough for me to produce a cover by a profinite set for which I can check this descendability. So we can reduce to, by pullbacks, we can reduce to K equals like 0, 1 to the n. And then I'll discuss just the case n equals 1 because it's simpler to write down. I guess I'm good that you can also reduce this case. What's that? Yes, that's true. By Kunith, yeah, you can also reduce to this case. Yeah, that's true. Yeah.
So this descendability means that when you take the homotopy fiber, you tensor, some high tensor power is 0.
Yeah.
Okay.
So there is some, yeah, we didn't get into much details about how to make these sorts of arguments, but Akil gave some toolkits, which are nice. So then in this case, you take the usual kind of Cantor set. So you have so I'm going to produce my cover of the closed unit interval by the Cantor set. So but let me write it in a specific way. So I'm not going to write, so a profinite set a priori, you want to write it as an inverse limit of finite sets, but sometimes you can instead write it as an inverse limit of compact Hausdorff spaces, and in the limit you just happen to get a profinite set, and that's the best thing to do here. So what we can do is we can take, the two halves of the closed interval, and their disjoint union is a space mapping to the unit interval. And then we can do the same thing again.
Yes, these are the base to the explanation of the.
Yeah. So then so then we have a sequence of spaces mapping to the unit interval where in the inverse limit you actually just get the Cantor set, which is then forming a cover of the closed unit interval. So what does this mean on the level of these push forwards? So the push forward from the Cantor set will then be the sequential colimit of the push forwards from each of these. Now, there's a general fact about this descendability that if you have a sequential colimit, it's enough to establish descendability with uniform exponent of nilpotence for each of the finite ones. And for each of the finite ones, you have descendability basically because you have a Meyer-Vietoris cover for the closed subsets. And the point is, the reason you get a uniform bound on the exponents is because in each case, there's only double intersections that you need to be concerned about and no triple intersections. So in the end, you get something like exponent of nilpotence 2 for each of these individual things, and then 3 or 4 for the colimit or something like this.
Each, and the composition of the individual thing is, when you have the individual thing, because I need to adjacent one, you have only adjacent ones, and then so when you divide it into k part, you claim that this is, okay, and I understand that when you go to power, like z, 0, 1 to some power, then the estimate will become worse.
Yes.
And therefore, like for the Hilbert cube, you cannot do it.
You can't expect anything, that's right. Yes. So this is where the finite dimensionality really comes in. So it plays a sort of a technical role in being able to ignore the difference between this and the derived category of sheaves of abelian groups, but this is really where you need finite dimensionality. Okay. Okay, now let's come back to the question about E infinity versus animated commutative. So now we have this object. Oh wait, is this going to work? Just a sec. Oh, maybe this isn't going to work. No, let's not come back to the question about E infinity versus animated commutative, with my apologies. Okay, let's actually... Right. So at the end of this, I want to make a remark.
Maybe it's good to say that at least in this example, this cover, we can endow fiber star by hand with an animated ring structure. Because then you only have to do it for idempotent algebras. Because it's a sequential colimit of direct sums of idempotent algebras.
Yes, that was the argument that's the argument I was going to suggest. And then I was thinking in my head about why for idempotent algebras it's automatic, and it wasn't quite clear to me. But I think you can do it by hand. I mean, if you knew the categorical structure, well, we should think more carefully about exactly how to do this, and report back next time. Okay. But let's move on. I want to make a small remark before we move on. So by similar arguments, or basically the same arguments, if you have a map like this, then, or sorry, if you were a functor like this, it's equivalent. A priori, you're saying that you have this connectivity estimate shriek locally on spec R, but it's equivalent to ask that. So over a proper cover, a cover by proper maps, you get the connectivity. So you don't actually have to, when you're worried.
I mean, there's an overkill argument which is to observe that modules over this give you a new analytic ring structure on your ring.
Could you say that one more time, Peter?
We don't hear.
If you have such a connected idempotent algebra over any analytic ring, then you can use this to define new notions of complete modules, which are modules over the sky.
Oh, yes. Uh-huh.
I think this defines like what you call a pre-analytic ring.
Yes, yes.
These are always analytic rings. I think it's way overkill. And there must be much way, but
that seems to work indeed. Yeah. But are all of the intermediate guys connective as well? Yeah, I guess they are. Well, okay. Yeah. So. Yeah. Okay. Or maybe connectivity isn't even important there anyway. All right. Oh, yes. And another remark is that this will actually be a little bit useful.
Somehow now I'm not lost.
I'm sorry. Oh, we're over here in the setting of number 2 in the theorem here. Okay. So let's say you want to produce a map like this by this procedure. So you want to produce a symmetric monoidal functor, and then you have to check this annoying condition that on some shriek cover of spec R, you have this connectivity condition. I'm saying, or I don't know, you have, I'm making a different claim, sorry. That let's say you have a map like this, then you know that shriek locally, you get this. But in fact, what we see in the proof is that after a proper map, even after just a proper map from a proper cover of spec R, you can ensure this condition.
This comes from after proving the equivalent.
Yeah. Not a priori. Not a priori, exactly. Yeah. Another remark is that if you have Z closed inside K, or this is actually more general, but and then U is the complementary open, then they are also each other's complements. In analytic stacks. So these two do determine each other. The associated analytic stacks do determine each other in the naive way, i.e., if you're given Z and you want to know U as an analytic stack, its functor of points is you just map to K such that when you pull back to Z, you get the empty analytic stack. That's the same thing as mapping to U, and vice versa. So that you can check on profinite sets, where it's quite elementary. Okay. So now let's get to.
Sorry, why did you write these intervals diagonally on top of each other?
How else did you want me to write them?
I was wondering what it means.
Doesn't mean anything. It's just because I wanted to write, for example, I wanted to write this one right above this one because I'm saying these two endpoints map to the same point down here. So I wanted to stack them vertically like that. Maybe that's the reason. Does that make sense? Yeah. Okay, so now we get to a topic that I think is fun, which Peter introduced last time. This is kind of norms on analytic rings. So let's say that R is an analytic ring. So definition is that a norm on R is a map of analytic stacks from the algebraic P1 over R, which is something you can build over any analytic ring by just base change from the trivial case with algebraic geometry, to the closed interval from 0 to infinity, which is a condensed set and thereby an analytic stack. So let's call this map N, and then such that. And then I'm going to give some conditions which are going to be different from the ones that Peter gave last lecture. So a priori, I'm adding an extra condition and maybe slightly rephrasing another of his conditions. And we don't know whether they're equivalent, but certainly we want all of the properties I'm about to list. So let's take this as the official definition now. Right. So the first condition is that, okay, maybe the first thing to remark is that such a norm function on P1 of R, well, certainly you can restrict it to A1 of R. You get a norm function on A1 of R. But then what does it mean when you have an element of R? Then do you get a real number or an element in 0 infinity? No, you do not get an element in 0 infinity. You get a map. So well, let me note if you're given an f in R, then that induces a section. So from P1 of R to spec R, then you get the section corresponding to f. And then you can compose that with the norm map, 0 infinity. And what you get is a map from spec R to 0 infinity.
Spec R in your
yeah, exactly.
Now suppose just to I don't know if this is a big detour, but suppose R, you start from an abstract ring. We said that there are several ways to view it as an analytic ring.
Okay.
And you can use the solid or no. I mean, anyway, there are at least 2 or 3 ways I remember. And then for each of those, you have a notion of norm. On the other hand, you have a norm like in Berkovich or things like this. So can you say what are the relations? So you have 3 analytic rings such and Berkovich, and what are?
Yes, we will discuss these things later, but I want to get the basic definitions in place first, and basic results and definitions. So yes, so a norm for an element of the ring, you don't get a real number. You get a map from spec R to the real numbers plus infinity. So if you can think of this as consisting of a family of residue fields, and kind of for each residue field you get a real number, but they could be varying with the residue fields, so to speak. Relatedly, if you have a norm on R and you have a map from R to R prime, you get a norm on R prime. So just by composition. So it's really, it's not like giving assigning a norm to each element in R. It's a geometric thing. So it's a geometric thing. You can pull it back and it still persists. So that's important to realize. Okay, right. So that's a prelude, and then the first condition is that norm of 0, which is a map from spec R to 0, 1 or 0 infinity. This should factor through. So factor through the terminal map to this is the
terminal analytic stack.
Terminal analytic stack. But it's also the analytic stack associated to the condensed anima, which is the singleton point, which is a subset of here. So this is a condition that the norm is the constant function 0. The norm of 0 is the constant function 0. By the way, in this geometric perspective, Ofer, there's something you might appreciate. There's sometimes this question of whether norm of 1 should be equal to 1 or 0 for the 0 ring. What is?
There are several purposes in the literature where there is one mistake.
Yeah. But this is avoided here, because when you have the 0 ring, then the norm is both 1 and 0, so to speak, because then this is the empty set, and then that map factors both through 0 and through 1. So if you take this geometric perspective on norms, you can never get messed up. It's not the same notion, but I mean, just to show. Yeah, yeah.
But still, it's...
Okay. Okay.
Wait, sorry, I have a
Yes.
question. So there's no, like, we're not saying anything about what happens to A1 of R.
Let me finish. So the second condition is that the following diagram commutes. So P1 of R maps to 0. The second and third conditions, I'm going to try to say the norm is multiplicative. The first thing I'm going to say is that it commutes with inversion. So here we have lambda goes to lambda inverse, which exchanges 0 and infinity. But we also have, let's call the coordinate in P1 t. Then we also have t goes to t inverse, exchanging 0 and infinity. And I want this diagram to commute.
So, by the way, the maps from anything to 0 infinity of a space like K or a compact is a set in your...
It's a set.
Yes.
It's just a set, yeah.
Yes, and even with any compact, okay.
Yeah.
This will set different things.
Yeah, any condensed set will go to an analytic stack whose functor of points is a set. Yeah. Okay. So this 1 and 2, so now note that 1 and 2 implies that if you take the infinity section, so let's say norm of infinity, so spec R, norm of infinity, 0 infinity. This factors through infinity. Okay, now before I, and now, okay, maybe 3. So set, I don't,
It also implies it's norm of 1 is 1, right?
Does this already imply that?
Points.
Yeah, okay, that's good. I was going to make that remark after the next one, but yeah, I guess it's already implied here. Okay, cool.
And also the norm of -1 is 1, by the same argument.
Okay. Yeah, thanks, guys. Okay. So 3. So I'll define, given a norm on an analytic ring, I'll define the associated analytic affine line to be the subset of P1 where the norms are a real number and not infinity. Then we have, then require that if you take A1 R analytic cross A1 R analytic, and then you have norm. Oops. Oh, I guess this is just R, but okay, I'll continue to write it as 0 infinity. Then here we can take the product, so, and we still get something in the region from 0 to infinity, which is contained in 0 infinity closed. Then On the other hand, this we can map to P1R cross P1, oh sorry, P1R period via multiplication. So TS goes to ST or TS.
This is defined. The multiplication map on P1 is not defined in general. TS. The norm inverse. No, why?
The analytic is contained here.
I'll make the remark. Yeah. So Peter is making the pertinent remark, which I'll justify afterwards. I mean, so yeah. So actually, yeah. Well, yeah. I'll justify why this map is well defined at the end. Right. So this map should commute. So that's saying that the norm is multiplicative, but as Ofer is pointing out, one needs to justify that such a map indeed exists. Let me do that now. So y TS goes to TS is well defined on A1N. So the claim is that so A1Rn is a subset, monomorphism admits a monomorphism to P1 by definition. Another thing that by definition admits a monomorphism to P1 is the algebraic affine line over P1. And the claim is that this one's contained in this one.
The algebraic affine line is you take the polynomial ring in one variable.
Yes.
Over
R, yeah.
Over R, and which, so in other words, you take for the condensed, you take just add polynomials in the stupid way, I mean, without any special. And the derived category is the things which are okay over R itself.
Yeah. So it's an affine analytic stack, this A1R, and it's just given by, again, keeping the same class of complete modules you already had in R and just adding the polynomial variable as operators. Why is this true? Yeah, so, right. So the point is that, so we want to produce,
so you have to check it on the two charts of P1R. One of them is already A1R, and the other one is the other A1R.
Yeah,
right. To somehow inverse the operator when you know that you are.
Right, so here's what I'm going to say. So we know that norm of infinity is equal to infinity. So what does this imply? So for infinity, we have, this implies that the infinity section of P1 is a module over, or an algebra over, is an algebra over, so norm upper star of the structure sheaf of infinity. Yeah.
One way to think about it is that it implies that this analytic affine line does not reach the infinity section. And then there's a general claim that if you have any scheme X and it serves a closed subset Z, and an analytic stack that meets Z trivially, then it actually factors over the open complement. But in the sense of schemes.
Well, a scheme is endowed with the trivial analytic.
This is trivial.
Okay, so let me try doing it the way, I think it's basically equivalent, but let me try doing it the way Peter was suggesting. So let's abstract a bit. Let's move infinity to 0 and abstract a bit.
Do it with like P1Z, so it means that you can do it with P1Z and then the usual scheme.
So suppose given an analytic stack over A1 such that if you pull back to 0 section, you get the empty set, so it misses the 0 section, then the claim is that this F factors through GM R. And it's part of a more general claim that Peter was making about a scheme and a closed subscheme, but okay.
Usual scheme with the kind of trivial analytic ring, analytic kind of, let's say usual affine scheme is the kind of the most trivial analytic.
Yes, yes. Right. Right, so F factors, and the reason for this is you can think of maps like this. Well, it suffices to treat the case where X is itself affine. And then maps like this you can think of in terms of symmetric monoidal functors. So if X is D of, I don't know, A, then you can think in terms of the corresponding pullback functor from D of A1R to D of A. And what do we know about this pullback functor? We know that it kills the structure sheaf of the origin. But then it's just a purely algebraic fact that if you kill the structure sheaf of the origin, then you factor through inverting the parameter. So the structure sheaf of the origin is just structure sheaf on A1 modulo T, the parameter T. So if you kill that thing, then you kill everything that's built from that via colimits. And so you don't see the difference between an object and the result of inverting T on that object. And then that exactly gives the factors through. Yeah, so thanks, Peter. I think that's a much nicer way of saying it. Everyone good? Okay. So that's the claim. And that implies that this map is well-defined, because certainly the multiplication is well-defined on A1, but so maybe then I put the A1 here a priori, and a priori have only the n going here. But then a posteriori, if I require this diagram to commute, then it follows that actually this lands inside A1 analytic, because by definition that was the preimage, because this map factors through 0 infinity. Okay? All right. Oh man. All right. I want to get to something fun. Yes, please. No, please.
So the fact that we denoted it as and, so the norms here should somehow correspond to, correspond to norms and the notion of analytification.
So I'm going to give some of the motivation at the end. But let me finish with the axiomatics.
Building on that, I remember last time, I think Press Schultz has said Gaga really was he noted down Gaga as as an isomorphism of stacks.
Yeah.
And somehow that was some sort of analytification. So does that also correspond to a norm then?
So this question, I suggest you keep it for later. Yeah. Let me finish with the axioms. 1, 2, 3. So 4. Okay, so axiom 4. Now, so maybe now's a time to say a bit about motivation. So what if you have an analytic ring? What we're going to try to do is we're going to try to say if you have an analytic ring, you want to try to build some geometry over that ring. But it's hard if you're just given an analytic ring and you don't know anything more about it, or you don't have any extra structure on it. It's kind of hard to build analytic geometry over it. I mean, basically all you can do is you can do this trick of importing algebraic geometry. For an arbitrary analytic ring, that's more or less all you know how to do. So what we're going to be doing And what's one measure that you have some good analytic geometry? It's that you have some nice subsets of the affine line. And nice in the context that we're discussing here means, for example, shriekable. So that the six-functor formalism works, and then it kind of really feels like you're doing geometry in some more or less traditional sense. But again, on a general analytic ring, you don't know how to write down any interesting shriekable subsets of the affine line. So you have to give yourself some of them. And that's the point of this notion of normed analytic ring. We're giving ourselves basically disks of some arbitrary radius inside the affine line. And they will turn out to define shriekable subsets of the affine line. And then we can get started on doing geometry that resembles some sort of traditional analytic geometry based on open disks or closed disks or what have you. But you have to have this extra structure on your base before you can get started on that game. If you don't have a notion of a norm on your ring, you can't start talking about closed disks and open disks of certain radius. So that's what we're doing right now. But we already have some sort of things that kind of seem to function as we've already seen certain versions of the unit disk. So for example, we've spent a lot of time discussing this basic module P, which recall was this free module on n union infinity modulo infinity. And of course, you can base change it to any ring, any analytic ring even. And so, well, what do we know about this guy? Well, we know it does have a map from R bracket T. So geometrically, so let me just, this is going to be not good notation, but let's set D equals spec P. So it's some version of a disk, and then dr will be the base change to R.
Again, you doubt P was a usual algebra structure, right?
That's right, yeah. And we've also discussed the algebra structure on P, which makes this an algebra map. So D does map to the affine line by this map here. But as we've also maybe discussed, so it's but it's not a monomorphism. So it's not really a subset of the affine line. So it's a proper map in our setting. So it's shriekable, but it's not a monomorphism. So it's not really a subset of the affine line. So what does it look like in examples? So in general, so we have this map from RT to PR. This induces an isomorphism on mod t to the n for all n. So this map, which is not a monomorphism, it is an isomorphism on the formal neighborhood of the origin. So at least in some sense you should expect close to the origin this is a monomorphism. And then what happens is it kind of blows up as you move away from, or it can potentially blow up as you move away from the origin. What? T goes to like the Dirac measure concentrated at 1.
How can you use the multiplication of n?
Or use the addition on n to give the multiplication on PR. Yeah. Right. So in particular, you get a factoring like this. So this, and so that's generally true that you have a diagram like this. Where this is the canonical map. And in most examples, so this PR mapping to RT is a monomorphism, is an injective. So in most examples, this lives in degree 0, and this map is an injection. So this is some kind of sequence space. And what is the condition that the sequence satisfies? Well, so in the abelian category, which is the heart of dr. So in most examples, this lives in the heart. This also, in most examples, lives in the heart. I mean, I guess maybe I should be using this notation, but I'm being a little bit sloppy here. Yeah, and then this is just an injection, so to speak. So in most examples, PR is like the set of sequences R0, R1, satisfying some summability condition. So such that if you term-wise multiply by a null sequence, you get a summable sequence. Where the notion of summability depends on the analytic ring structure. But at the level of this discussion, you could imagine, for example, R being the real numbers, and summable means usual absolute sum the absolute values, you get a finite number. That's not actually a special case, but it's close enough, and it serves the purposes for this discussion. And this is kind of just by the universal property of PR that this is the correct interpretation, because PR maps out of PR to an M in dr. These are supposed to correspond to null sequences in M by construction. You know, it's the kind of thing which, when paired with a null sequence, you get an element in M. And so the idea is this procedure, yeah. So when you have a null sequence, and then, yeah, well, I'll let you. maybe me trying to explain it is not as helpful as. Helpful as all that. R is any analytic ring, I don't know. But this is not precise mathematics here.
Yes, but in this norm business, R is just a discrete ring. In this norm.
Well, no, in the norm business, R is an arbitrary analytic ring. Yeah.
M is then PR is a. Okay, so you say that usually it's as an object in the abelian category of R or more.
Yeah, usually that's right. Yeah.
And this is what you call M.
M? Oh, sure. Well, I mean, yeah, I could. Yeah. I mean, so I was saying that this is the interpretation you get in practice, where the notion of summability depends on the analytic ring structure. And the way you see that this is the correct interpretation is by thinking about what it means to map PR to M. And so, like, for example, the most basic thing would be if you map PR to R triangle. Then that's the same thing as giving a null sequence. But then if you think in terms of what happens when you restrict to here, you have if you have some coefficients in a polynomial, so if it terminates, if you have zeros after a while, then what you're doing is you're just summing the null sequence times those things to get an element in our triangle. And then you imagine that this is saying that summing should make sense for something which is not necessarily eventually zero. And so this is kind of the interpretation you should give that. Right. And what, so if, for example, R is C with the gaseous or liquid analytic ring structures, what you see is that you have, if you look at holomorphic functions on the usual ring of holomorphic functions on the closed unit disk, meaning they overconverge on the closed unit disk, then then every one of those satisfies this. If you look at the coefficients of the power series, it will satisfy this summability property because your power series has a value at 1, so the sequence of coefficients better be summable. So you'll get a map like this. So this summability condition is weaker than the condition which defines these things, but it's stronger than the condition which defines a holomorphic function on the usual open disk. So if you think in terms of your usual complex analysis, then that's where your P is sitting. It's sitting somewhere between the open disk of radius 1 and the closed disk of radius 1. And that's the kind of behavior we're going to be axiomatizing in condition number 4. Yeah, so this is something like exponential decay, and this is something like exponential growth, and this is something like summability. So it kind of makes sense that it's in between the two. Okay. It was a bit of a long-winded explanation.
Sorry, what's condition 4?
I haven't written it yet. I've just given motivation. But yeah, so what you want to think is in these kinds of normed analytic ring settings, this, well, okay. So then condition 4 is, so condition 4 is split into 2 parts. Well, the first part is that if you have D mapping to P1, or dr mapping to P1 are mapping to 0 infinity via the norm, you want this to factor through the map to 0, 1. That corresponds to this, saying that this notion of unit disk is sandwiched between closed and open. But you also want that this, if you take dr mapping via the norm map to 0 infinity, and if you pull back to 0, 1, the open, or the half-open segment from 0 to 1, then you should get an isomorphism over here. Sorry. Yeah, so norm inverse of 0, 1. Sorry, shoot. I need P1 to be in there. Thanks, yeah. Oh, sorry, norm. So then we have so I want that, yeah.
You wrote an inclusion there. So.
Sorry? Oh, I didn't mean to write an inclusion. Thank you, yeah. Thank you. What I want to say is that, so this, yeah. Well, let's say this map is an isomorphism over the locus given by the open unit disk. So this is like some sort of proper map which blows up along the boundary of the open unit disk. But on the interior of the open unit disk, it's an isomorphism. So this is something stronger than saying that you have a map like this. And the nice thing about this stronger condition is, first of all, you can check it in practice, and second of all, it's just a condition, whereas giving a map like this is a priori structure. So.
Can I think of this norm to be some non-Archimedean norm?
You can think of it as non-Archimedean or Archimedean at will. We haven't enforced any compatibility of the norm with addition. So it's, yeah.
So I want to put the last condition last time.
Yeah, so this is...
And it is automatic if you look over the real numbers, for example.
Right. So the so this was the cosmetically I changed the discussion of multiplicativity from Peter's lecture. That's just a cosmetic change. This is potentially more serious. Peter did not mention this axiom last time, and we're not sure whether it's a consequence of the other axioms. But yeah, as Peter mentions, if you're over a base which solidifies to 0, so for example, if you're over the real numbers, then you can prove this from the other axioms. But we're not sure whether, which solidifies to 0. It means when you base change to solid, if you base change spec R to spec of solid Z, then you should get the empty analytic stack. if that condition is satisfied, then this condition follows from the other conditions. But
so can you give example of things that solidify to 0?
yes, the real numbers solidify to 0. So any analytic ring where the underlying ring is an algebra over the condensed ring R will have that property.
So again, so you have something going to spec Z solid. But all the non-Archimedean things from Uber rings are not solid. Okay.
So over there, potentially so as far as we know so far, there could be some weirdo norms which don't satisfy this condition, but yeah, they're not any of the usual ones. The usual, well, yeah. The ones that don't satisfy this, unless it's some really extremely interesting new mathematical phenomenon, which seems unlikely, they're probably just very pathological. We're taking this as an axiom, okay? And then you could ask the question whether it follows from the other axioms. Okay, so what is a norm? Again, so what is a norm giving you? So if you have a norm on an analytic, so these are the axioms. So this gives you, so again, in terms of the discussion of maps to compact Hausdorff spaces, this gives you for every, for example, you get norm upper star of the constant sheaf on 0R. So if you take R non-negative real number, then you get this idempotent algebra in D of P1R. And this, of course, the interpretation of this should be over-convergent functions on the closed unit disk of radius r. And the over-convergence, it has to be over-convergent. There's no other possibility because note that the constant sheaf Z0R is the filtered colimit of the constant sheaf 0 R prime for all R prime bigger than R under the restriction maps. So the overconvergence has to be built in. Like if you imagined that you were sending this to some version of functions on some version of the disk of radius R, some version of the disk of radius R, then that version would be forced to be the overconvergent one because of this property here.
And because that number star commutes with colimits.
And because, yes, because it's a pullback functor, so it commutes with colimits. All right. And OK, so and actually the data of these guys, given the axioms, this determines n. Because it's very easy to classify the closed subsets of this interval, and you only need to know about things less than or equal to something and things bigger than or equal to something, but the axiom about inversion gives you one in terms of the other. So you just have to give these things subject to some simple conditions in order to specify a norm. OK. So the next topic is classifying norms. And I mean, I don't mean like as in classifying space or whatever. I mean how to classify norms on a given analytic ring. Yeah. So let me start with one a lemma here.
And I have a question in the chat whether there's a norm on should be solid that requires the usual over-convergent algebras.
Yes, and yes, there is. Yeah. Right. So lemma, so given a norm on an analytic ring, so a norm
maybe we could just say, you just said what data you have to give to define a norm, and you can just check that the usual argument algebra is neither non-Archimedean geometry or non-Archimedean geometry over QP solid or the complex numbers with the Gettius or liquid ring structure, they do satisfy this axiom. So this way you can deduce by hand now such norms over QP or with complex numbers.
Right.
Sorry, but what does overconvergent mean?
It means, so an overconvergent function on a disk of radius r means a function which converges on some disk centered at the same point with larger radius.
Oh, okay.
Yeah, so it extends to a function on an open neighborhood of the closed disk. Right. Yeah, don't be shy about asking such questions about terminology because I know, yeah. Well, anyway. Right, so given a norm, then you can look at the locus of the locus where the norm is strictly between 0 and 1, and this projects down to spec R, and I'll say that this is a cover in the Grothendieck topology we've been considering. So i.e., if we're willing to work locally, we can assume we have an element you can call Q in the underlying ring such that norm of Q is in, so to speak, or lies strictly between 0 and 1.
So is it the case that when you take any real number?
Yes, yeah. So actually, so I'll make a stronger claim in the proof. In fact, if you take norm inverse of say 1/2 spec R, this is a cover. And that's a stronger claim.
Is a cover in the Schrick?
In this Grothendieck topology, the only Grothendieck topology we've put on our category.
Okay, but this is the strong side of the map is Schrickable.
No.
Or that it's a cover?
No, it's a cover in the Grothendieck topology.
That it can be refined to a Schrick?
Yeah, in fact, this is not necessarily affine.
Okay. The cover in the sense can be refined to...
Yes.
Can be refined.
Yeah. But that said, let me for simplicity assume that this is affine. So there's an argument for getting the conclusion anyway, based on again resolving this by a profinite set and using that descendability that was proved earlier. So, but I'm going to skip over that part of the argument. So, for simplicity, assume so that this norm upper star of the constant sheaf on 1/2 is connective, so that this norm inverse of 1/2 is affine, and it is and it's actually proper over A1. It's just given by this algebra, and hence over spec R. So in that situation, this is both affine and this is affine and it's proper over spec R. So by this descendability criterion, we need that our triangle lies in is generated by this algebra. So but what I claim, our triangle is actually a retract. directly a retract without any cones. And so implicitly, I'm viewing this over the affine line instead of the projective line. And then, I mean, I take the forgetful functor from d of a1 to d of r when I write this here. Or in other words, this is descendable of index 0. So it's like the descent is quite direct. You just take a retract. And then the intuition behind this should be clear. This is some version of a Laurent series ring. It's a Laurent series ring in variable t with some convergence condition. And you can just pick out, say, the 0th coefficient of your Laurent series. And that gives a linear map, not an algebra map, but a linear map which splits the unit. That's the idea, but we have to make sure it holds in this completely abstract setting here. So what you do is you can take the structure sheaf of P1, and then you can take the norm upper star of Z. Well, yeah, well, okay. So this is a pullback in D of P1. Just because the constant sheaf on this interval is the pullback of the constant sheaf on 0, 1/2, constant sheaf on 1/2, 1, glued along constant sheaf at the point there. And then we apply push forward to D of R. Then the cohomology of the structure sheaf on P1 is just R concentrated in degree 0. So what we get we're R triangle. And then I'm going to use the same notation. So the same, these ones live over A1, or this one doesn't, but, well, whatever. Just push it, well, it lives on the other A1, but we can just push it forward. Copy the same guys over there.
First, twist by -2 to make cohomology degree 1.
What's that?
Don't you first do a twist by -2 to get cohomology degree 1?
Why do I want cohomology in degree 1?
Because you want the map from n upper star Z1/2 to.
That's not the way I'm going to do the argument. So yeah. So what I'm going to say is that so this is then a pullback in dr, but it's also then, well, pullbacks are the same thing as pushouts. So it's a pushout in dr. So if I want to make a map from here to a certain place, for example, to R triangle, I make a map here, and I make a map here, and I make sure they agree there. So what I do is here, I take evaluation at 0 from R which goes to R triangle. Here I take evaluation at infinity, which also goes to R triangle. And then they clearly just both give the identity map when you restrict to R triangle. So this gives the map here, which when you restrict back to here is the identity. So that that produces the desired retraction. Oh, kind of. Yeah.
And what about this connectivity restriction?
Oh yeah. So then what you have to do is you have to see that. So there's then you have some. It's not if it's not necessarily affine, that you still have some proper cover by something affine. And then and not just proper but descendable. So then the unit here is generated by the image of this. And it follows then that by combining the two generation claims, the unit here is generated by the image here, and that provides the desired refinement by a Schritt cover of affines. So you take any proper map to here, which makes the thing connective, which I explained why exists, then this map will be a Schritt cover because the push forward will generate the unit because the analogous claim is true both here and here.
And in the first arrow, it is true because of the
argument we gave in the first half of the class, yeah. by this descendability of Cantor set mapping to the unit interval.
Which was but n inverse 1/2 is where is the unit interval of, no. It's you apply you cover 0 infinity like you did, and you look at what it gives in this. No. Sorry? You want to get affine things. You said that n inverse 1/2 is not affine in your terminology in general.
Yeah.
So how do you make it affine by?
It's not a pullback on the base. It's not by working locally on the base. It's by working locally on P1 or A1. It's by working locally on A1 using the previous argument. So A1 maps to 0 infinity. So then there exists a proper cover of A1 by an affine where that map factors through the Cantor set. And then that will give you the desired connectivity and also descendability there.
You have descendability
Yeah.
first.
Yeah. And you have descendability both here and then by that argument here. And then this is affine and proper. And yeah. Okay. Right. So now let's give ourselves this extra data which we've assured can be gotten locally. So given a norm P1R norm 0 infinity and a Q in such that so the claim is that we can think of Q as being given by a map from so Z bracket T to our triangle or to R. Why not? So T goes to Q. Claim this factors uniquely through this gaseous base ring. Let me not name the map. Let me call the variable Q here, and so a variable which the norm makes look like it's topologically nilpotent actually has to come from this gaseous base here. So the proof is, so let me start with the uniqueness, which has nothing to do with norms. It's actually a claim that, so spec, the claim is that spec Z Q hat plus or minus 1 gas, which maps to the affine line over Z, say, this is a monomorphism. Yeah, so that's the uniqueness claim, or a strong form of the uniqueness claim. There's there's a contractible space of factorings if one exists. This is not obvious from the definition of the gaseous base ring, because by definition of the gaseous base ring, we took this ZQ hat, which was just P, and then we inverted Q, and then we enforced this Q being gaseous. And this is not idempotent, so not idempotent. So enforcing the condition of being gaseous defines a monomorphism on the level of analytic stacks, because it's just some quotient of categories. But because this is not idempotent, it's really not clear from that description that the composite map all the way to A1 should be idempotent, because it seems at first you have to choose something which is extra structure, namely a proof that Q is topologically nilpotent, so to speak. But you can do it in the other way instead. But you can also think of this as modules over P, or P modules in, you just take a polynomial ring in one generator and make that generator gaseous. Oh, and then maybe I have to invert Q too. Well, okay, let's just. So. And then the claim is that P is idempotent in D of Z Q plus or minus 1 gas. And this actually, so we want to check that P tensor P equals P. That's actually a claim that happens after base change to P, so to speak. So it actually reduces to a calculation here. That if you take this P over Z Q hat plus or minus 1 gas, now we have both a Q variable and then we have a T variable, say, coming from the P here. That if you take this and you mod out by T minus Q, you just get the underlying ring. So.
Yes.
Yes?
You should still write a guess because the completion changes the underlying ring.
Oh, okay, sure, yeah. I meant, the underlying ring of the analytic ring structure. And Peter described this, this free module, and if you use that description, you will find yourself, you have to check a short exact sequence, and you can do it. So that's the uniqueness. As for the existence, well, let me just say it in words. It's fairly elementary from the definition of the norm. So because our norm is contained in here, this means that we're away from, so existence. So norm of Q contained in 0, 1 means we're away from norm inverse of 1 infinity. And that in particular means that we're away from the opposite, well, let's say the D sitting at infinity. So if you take this D, the thing that was spec of P, and you translate it to infinity on P1, then that's going to be contained in this locus. But then saying that you're away from the D setting at infinity is exactly the same thing as saying that Q is gaseous. But then on the other hand, norm of Q contained in closed interval from 0, 1, because of the axiom, I'm referring now to the axiom 4 about the placement of D in this, under this norm. This implies that Q comes from D, so Q is topologically nilpotent. So it comes from D. So D was this spec of P mapping to the affine line. It therefore maps to P1. And then you can pull back that map under the automorphism of P1, which is the inversion map. And you get something abstractly isomorphic to D, but the structure map to P1 is different. Okay, so D around infinity. Yeah. Okay. I'm almost done. I apologize for going a bit over. So So now let me state the main result about.
What is comes from D?
Comes from D means that it promotes to a P module. So well, what I mean is that Q. So Q is a, What I mean is so Q is a section of this projection. Well, it's a section of this projection, and the claim is that it factors through D. And the reason is that it factors through the norm inverse of this, and one of the axioms guarantees that implies that it factors through D. Yeah. Yeah.
Have you stated what the classification is of?
I'm doing it right now. So theorem. So for given an analytic ring R, there is a bijection, natural bijection, or the map from the set of pairs, well, not really set, but okay, n. This is a norm on R, and then a Q in R such that norm of Q is contained in 0, 1. So up to a cover of spec R, this is, we can assume we have this data. So up to some cover, we're classifying all norms. But then from each of these, I've just said, you get a map from spec R to, well, first of all, you get a map to spec of Z Q plus or minus 1 liquid. But then you also get a map to the open interval from 0 to 1.
Yes, it's not liquid.
Oh, thank you, gaseous, yeah, thank you. And this is by recording Q and the norm of Q. This map is an isomorphism. All right. i.e., giving a norm on an analytic ring plus an element of norm strictly between 0 and 1 is the same thing as specifying what the norm of that element should be, which is this function here, and requiring that Q actually come from this gaseous theory that we discussed earlier.
And both sides are sets?
No, almost. Well, except for the annoying fact that A1 is not a set. So, so
the norms and Q, the first thing we said is that the norms really is a set because there is no, and the Q of course is something in some set. And
no, the Q is not in a set because this could be derived. So both of these map to A1, and like sort of the fibers of these maps are sets. So they're as much sets as each other, but they're not each individually sets.
So Q is a derived. Okay. But you still think of Q as choosing something in the zeroth part of the simplicial.
Zeroth part, yeah.
In a derived, implicitly the higher things, the higher maps are there also.
Yeah.
So it's not, you have to construct them as well. Or they come automatically from the form, I don't know.
So let me give the proof.
Only describe non-active equivalence.
Not now. So the proof. So after a descendable cover, we can assume Q admits all power, admits and compatible. nth roots for all n. So i.e., so this is because this is descendable, so it's countable in FPQC. So we're free to, because both things are sheaves in our topology, both sides are sheaves in our topology, we're free to work locally, so we're free to assume that Q has all nth roots. Then the claim is that so write dq for the pullback. So we have d going to p1, or let's say a1, and then we have multiplication by q on a1, and then we have dq here. So for this makes sense for any q in GM. Note that if q equals q, sorry, I apologize. Maybe I say d alpha for alpha in GM. But note that if alpha equals q times beta, where q is topologically nilpotent, then we get a map from d alpha to, oh, and I have to get it going the right direction. So d alpha to d beta is one of the two, which is also induced by multiplication by q. So here you use that this p is a Hopf algebra encoding multiplication. So, right. I may have gotten the ordering wrong. So this is some disk now. This is some disk of radius q inverse, or some version of a disk of radius q inverse. It's not the correct one because it's not a monomorphism and it blows up along the boundary, but then we can fix that. So dq, or d alpha, sorry, gives a disk of radius, a kind of disk of radius alpha, of radius alpha inverse maybe, and the maps above give the inclusions between such disks.
What about this? You discuss.
Transition about just the identity, so to say.
I'm sorry?
Do you really want multiplication by q as a transitional, or really the identity, so to say?
What do you mean, the identity?
No. You have a map.
For example, epiconic map to A1, right?
Yeah.
And as a multiplication by q map. Okay, maybe I'm not sure what the map to A1 is considered right now.
Yeah, I think I'm saying the correct thing, but yeah. Okay, but now we apply this to like alpha equals q to the m over n, so m over n in the rational numbers, and we get disks of radius. Norm of q to the m over sorry. We can assume. Sorry, the first thing I should have said is we can freely assume that the norm of q is constant equal to 1/2 by rescaling the norm. I feel like I'm not. Peter, what just happened? This is crazy. I literally just repeated your lecture with more detail, and I didn't get any farther. I thought I was going to get farther. I'm sorry for that. So I think we have to do a better job with the organization. I don't know. But okay, so you get disks of this radius and inclusions between them. But then you do this over-convergence. So then you use these to make the over-convergent versions. For an arbitrary real number, you can look at all the rational numbers bigger than it. You have these kind of fake disks of that rational radius. And then in the co-limit, all these problems about blowing up along the boundary disappear, and it turns into the thing which has to be specified if you're given a norm on R. So when you make this over-convergent, it will be forced to be equal to the thing that comes from a norm if you have a norm. So that's more or less an argument why this is a monomorphism. And then if you want to check that it's a bijection, you just have to produce a norm on here, and you do it by following this procedure, or a norm on here, and you can even adjoin all the roots that you want. And then you do it by following this procedure. So yeah, so you take this fake disk, you translate it around by multiplication by powers of q, and then you build the inclusion maps between those disks. I don't mean translate, I mean expand by multiplication. You build the inclusions between those disks, and then you make them over-convergent, and then you check that you have all the axioms. So yes, sorry for going over time. Thanks for paying attention.
So in this inclusion of this using Q topologically imposed, we also had an analog and discussed Huber rings of power bounded.
Oh yes, yes.
If Q is power bounded,
yes.
Does it still follow that you have an inclusion or not? Well, maybe you need to work in a more restricted, solid context there. But
no, it's a good point. Yeah. It's not. I mean, it's not entirely clear in this general setting what the class of Q for which you get such a map is. Yeah, let me say. Because I mean, for example, this argument here doesn't prove that you have an identity map. When Q, like I wasn't allowed to take Q equals 1 here, but obviously you can take Q equals 1. So I obviously haven't made the best possible claim, but. Yeah.
But for example, if Q is a root of unity, okay, for roots of unity we know that the norm is 1, I guess. We said it from plus minus 1.
I did.
Do we know it for any?
I did skip a step that you're exactly pointing at, which is that let's say we've said that norm of Q, which is a map from spec R to 0 infinity, let's say that we've arranged that this is 1/2. Then the claim is that if you have a Q1 over n, then its norm has to be 1/2 to the n. Yeah. So one inclusion is obvious by just writing down the diagram with the nth powers, and then you can prove the complement. You can prove the other inclusion by passing to the complementary opens and running the same argument there. What's that?
Half to the 1 over n.
Oh yeah, whatever the right thing to write down is. Yeah, thanks. Yeah, yeah.
I mean, it's just that in both the real numbers you can take x uniquely, right?
Yeah, but you have to. But I do think you need to invoke this fact that the closed and the open are the complement of each other to. Like with writing down diagrams, you only prove one inclusion.
But you have the nth power map on P1, I guess. Yeah. And then you prove that the diagram commute because you use the both alpha and pieces.
Yeah.
And then you consider the pullbacks and get it directly, but I'm not sure if this would work.
Yeah, I think it follows from a direct diagram.
Does it? Is it? Oh.
I think you need to take n screws.
Because this is a terminal object, or I don't. Well, anyway, it's true.
That's right. That raising to the nth power on P1 is right on the diagram. Yeah, I think it follows.
Well, okay. You're probably right, but let's try. Okay, norm. Ba. Maybe you're right, yeah. I mean, I was thinking about, yeah, I don't know. Yeah.
So it keeps monorail into a section upstairs.
Yeah.
It goes to downstairs to a section given by the Q.
Yeah.
So the spec over a half. But then if you take the callback on the right of a half, then this is just.
Yeah, that's true. Yeah. Okay. Yeah, okay, good. So there's no subtlety at all, but you just directly check that the nth root of Q has to have the norm given by the nth root of the norm of Q. Okay.
So say that roots of unity go to.
Yeah, that implies in particular that roots of unity go to 1, yeah. Okay. Yeah, see you on Friday.
So what's the intuition for like not being able to do geometry unless you choose a norm?
No, I don't want to make such a strong claim, but I mean, if you want to do some geometry,
What would happen? Like if you didn't fix.
Wait, but can I try to answer the question? Because what I meant was, because I have to clarify what I meant. So that if you want to define a notion of geometry that somewhat resembles usual complex analytic geometry, which is in the end based on open disks, closed disks, and so on, then you need to have something that measures the size of a radius of a disk. And that's what the norm does.
But isn't it kind of like packed already when you fix the base field? Or like it will change, or are there like, is there more than one complex analytic geometry based on the norm? Like basically, I think this is related to the question about the equivalences, like equivalent is up to like the geometry that will arise, or?
I mean, you could choose different norms. I mean, obviously there's a conventional norm on the complex numbers, for example, but.
But with the fact that there's more than one, at least in principle, would mean that it's not the usual complex analytic geometry.
I mean, you get something basically equivalent. So I mean, you could scale the norm is something you can do, like scale the norm by some alpha. You get basically the same geometry. So actually, one thing we're going to do is we're going to mod out by, at some point, we're going to mod out by these sort of exponential rescalings of the norms. When you do that, you can't talk about a disk of a fixed radius, but still many other things work okay.
Ring,
yeah.
We discussed this many times. So if you have a pseudo-uniformizer,
Yeah.
you choose, let's say, absolute value Q standard 0 and 1,
Yeah.
then you get a norm on this, and in particular in each residue field,
Yes.
you get a norm, a non-Archimedean norm.
Yes.
And this is like choosing this collection of non-Archimedean norms.
Yes.
So it is not at all the same as like, so let's say for an Archimedean field, it's related to the previous notional norm, but for a more global object, it is very far from like the Berkovich space and so on, which just chooses one of them. It's quite different. That's a way to uniformly think of norms, so this is the intuition.
Yes.
And so you and presumably what I said is an equivalence for Tate-Huber rings. The notion of norms in your sense is the same as a way to, of course, you can choose it continuously.
Yeah, exactly.
Continuously on the Berkovich space, you rescale a given one. So it is a torso under the scaling of the fixed one.
That's precisely correct, and it sort of follows from this.
Okay. So in this example, this is what you get.
Exactly.
And of course, then you can. And of course, for other analytic Huber rings, just locally you can do the. I mean, you can. And for non-analytic Huber pairs, this is something different.
Well, it's ruled out. Actually, I mean, you have to be Tate. You have to be analytic. I mean, we were saying Tate instead of analytic in this class. But you have to be Tate by this result. If you have a norm, I mean, then locally,
for discrete guys, you are not having any non-trivial any theory of norm.
Exactly, that's right. But what we're going to see is that if you mod out by rescalings, then there's a way to extend this. So when you mod out by rescalings so norms form an analytic stack, by the way. So it fits the definition of an analytic stack. So sending R or spec R to the set of norms on R, that's an analytic stack.
And you have to prove it's covered by something.
Yeah, I just did. Yeah.
Okay.
Yeah.
Okay, so the norms is an analytic stack in yours there.
Yes, it is such that like discrete Huber things can't map to that stack, but there's an enlargement of the stack which also accommodates solid Z and anything living over solid Z and so on, which we'll probably discuss.
So there was this thing like in the theory of diamonds and so on that you want to get from an analytic, like in the p-adic setting, you get a diamond from an analytic Huber pair. But if you have a non-analytic, still you can look at maps of analytic affinoid to it and then get a down kind of. There was this non-quasi-com, I forgot now how it, maybe it's not related to this, but somehow looks a little.
I'm not sure what you're referring to, actually.
No, because there was a non...
I work on diamonds, I somehow only allow Tate rings as test objects. So even if you start with a discrete one, I still only remember how Tate things map. Thanks.
Okay.
It's a perspective. Also adopt now more globally, not just gameplay, using this perspective of restricting to non-analytic rings.
Could you repeat that comment, Peter? The sound wasn't so great.
Yeah. Okay. I'm not sure if you hear me better.
Yes.
Well.
Absolutely.
I was saying that in my work on diamonds, I only look at how Tate rings or perspective Tate rings map to something. And even if I start with a discrete ring, I only remember these kinds of things. And so using this notion of non-analytic ring, one could now similarly restrict to non-analytic rings and look at stacks only from their perspective, which may or may not be something one might want to do globally. But right. It's kind of analogous to that.
Right. Yeah, so so I guess in this diamond setting, Peter proved some results saying that even for a discrete ring or something, the knowledge of how it maps to perfectoid rings gives you maybe quite a bit of knowledge about the discrete ring. There's a similar phenomenon here where actually, you can actually use normed analytic rings to, you can basically recover everything just from the functor of points on normed analytic rings. But, yeah.